Hello, Jake. Before I talk about, you asked about magnetism, and before I talk about that, I'd just like to have a bit closer look at Einstein's proof, because I don't. There's something about it that I didn't make clear. Possibly. You probably possibly understood it anyway. Okay, so we've got two triangles here. This one, which represents any old triangle, and this one, which is a right angle triangle. And so what I'm talking about this one, what I'm about to say about this one is true for any triangle at all. We take a triangle and we draw from one apex the perpendicular to the other side. That gives us two right angles. And then we got, because of this, we then got two triangles in area, two areas which add up to the area of the bigger triangle. Now each of these three triangles, the smallest, the middle-sized one and the bigger one, the biggest one, each one has its area is the ratio, the area of each of the triangles and its square belonging to it. There is a ratio in areas between the triangle and the square. And so there's a ratio between this, the area of this triangle and the area of this square. There's a different ratio between the area of this triangle and this square, and there's a yet different ratio in area between this, the biggest triangle and the biggest square. And I can write this ratio, or I can write the area of this smallest triangle by saying that its area is equal to a squared divided by some number k, say. And we can do the same for the other two triangles. So this middle-sized triangle has area b squared divided by some number L, say. And the biggest triangle has area c squared divided by m, say. But we can't say that the area, we can't say that these two areas add up. Well, yeah, we can say, what we can say that this equals this. Yeah, we can say that. But this does not give us Pythagoras, because we've got these three different numbers. On the right angled triangle, again we have the same sort of thing. Well, yeah, but so there's a special case where each of the three triangles is exactly the same shape. They might not be the same size, but they are the same shape. They're similar. and that means they're scalings of one another. So so to get from one triangle to the other, you can multiply its size by some number to get the other triangle. You can't do that here because no matter how, say with this triangle, you can't just increase its size to get this triangle. They're different shapes. And so if we've got A, B, and C again, we can do the same thing as we did before, except that the three numbers, the ratio of this triangle to its square, and the ratio of areas, that is, area of this triangle to its square, and the ratio of the biggest triangle to its square, all these three ratios are all the same because they're all scalings of each other. If we take this shape here, we can scale that exactly to the other two by some multiplication factor. So that, because of this, the three numbers are all the same number. We know that the areas of these two triangles add up to the area of the big one. The area of this triangle plus the area of this triangle adds up to the big area. But in this case, we are able to cancel these numbers to end up with how about that then? Okay, thank you.